This is the circuit for the unity gain buffer. The potentiometer is connected over here for stability. The white wire is V in, the blue wire is V out, the green wire is V minus, and they connect to their respective analog inputs A0 through A2. Op amp is located here, and this is powered by the 5 volts on the Arduino and grounded also on the Arduino.
This is the unity gain buffer shown in processing for Lab 7. As you increase V in, V minus, and V out both increase to be at pretty much the exact same voltage, except for when you go down to below 2 volts because the op amp is not connected to a +5 and -5 volt source, so it ends up saturating at about 2 volts. This means that the unity gain buffer is working almost exactly as intended, except for obviously the saturation.
This is the inverting amplifier circuit. The potentiometer is connected over here for stability. The yellow connections here are going to V plus. The green connections here are going to V minus. The white connection here is going to V in, and the blue connection here is going from V out. They all go into the analog sources A0 through A3. The breadboard is powered by the 5 volt power from the Arduino. It is grounded on the Arduino, and then these orange ones are jumpers to get from V out back to V minus.
This is the inverting amplifier. As V in varies around the virtual ground of 2.5 volts, V out varies from 3.5 volts to 2 volts with around a -10 gain. V minus cannot be kept at a virtual ground because V out plateaus, but when V out is actually being amplified when V in is very close to 2.5 volts, V minus is indeed the same voltage as the virtual ground, which is 2.5 volts, which is pretty much what we did expect in this scenario.
This is the integrator circuit. The potentiometer is connected over here for stability. The yellow wires are going to V plus at 2.5 volts. The green wires are going to V minus. The blue wire is going from V out to analog 2. And the white wire is going from V in to analog 0. The breadboard is powered by the 5 volt strip from the Arduino. It is also grounded on the Arduino. The capacitor is here, which is jumped by these orange cables to where V in is with the appropriate resistor.
This is the integrator circuit. As V in varies around the virtual ground of 2.5 volts, V out varies from 3.5 volts to 2 volts with around a -20 gain. V minus again cannot be kept at virtual ground because V out plateaus, but when V out is being amplified correctly, when V in is very close to around 2.5 volts, V minus is indeed the same voltage as the virtual ground. The main difference between this and the inverting amplifier circuit is due to the capacitor discharging. It takes time for V out to get to that plateau, but this is pretty much exactly the behavior we would expect. These are the derivations for problem 1 and problem 4. The first one is Kirchhoff's current law, where since V minus is the same voltage as V plus, you can say that V out minus V in over R2 is equal to V in minus 0 over R1. And then after you do some algebraic rearranging, you can see that the non-inverting amplifier gain would be R2 over R1 plus 1. So for 4, you apply Kirchhoff's current law, and again, since V minus is the same voltage as V plus, we can say that 0 minus V out is over the complex impedance of the capacitor, J omega C, is equal to V in minus 0 over the value of the resistance. Then with a little bit of math, we do find out that V out is equal to -1 over J omega RC, V in. Since J omega is equivalent to an integral sign, we can change that to V out is equal to 1 over -RC of the integral of V in with respect to time, thus giving V out a quadratic relationship with time in respect to V in, and so making it take longer to get to its final values. This is the processing code for exercises 2 and exercises 3 and 4. They're pretty much exactly the same, except for that these 4 variables here are multiplied by slightly different numbers. This is because this needed to vary around the artificial ground of 2.5 volts and had negatives involved, whereas this one did not. Otherwise, these are pretty much exactly the same as the oscilloscope used in Lab 5. This is the Arduino code for Lab 7. This is just a bunch of pins. These are variables that will be used later. This is initializing every single pin as an input. This starts the serial monitor. This reads all the pins. This puts all the pin data into a string. And then this sends that string to the serial monitor every 50 milliseconds.